Hi, and welcome to the Graphisoft EcoDesigner Star Energy Efficiency Building Design video series. This movie is entitled Low Energy Demand Architectural Design, and it shows you how to optimize the building project so that the conditions inside meet the internal comfort requirements as often as possible without the help of any building systems. We'll proceed according to the following workflow. Start by creating the baseline building reference file. Apply the project-specific low-energy architectural design solution set. Run demand calculation that contains performance rating. Review the energy efficiency benefits of architectural optimization. To enable comparative evaluation of a building project, it must be documented in its baseline building design state first. Please watch the project-specific low-energy building solution set movie clip to find out more about the baseline building concept. Here is the 3D view of the baseline building model in ArchiCAD. The energy model of this project is detailed in the previously mentioned movie clip. Its thermal blocks are listed with their relevant properties on the Energy Review palette and can also be visualized in the 3D view. The thermal characteristics of the structures and openings are also defined. With all the inputs ready for demand calculation, it would be possible to execute a successful energy analysis on this project using EcoDesigner Star, but let's save it in the baseline building file format instead. The next step of the low energy demand architectural design workflow is to apply certain sustainable design solutions to the project. The baseline building energy performance is used as a reference point to help put the designed building's energy performance into perspective. In the movie clip entitled Project-Specific Low Energy Building Solution Set, the most appropriate low-energy design strategy was determined for the example building project. In this movie, the next step of the sustainable building design workflow is demonstrated: how to implement the project-specific low-energy building solution set on the ArchiCAD virtual building. The following architectural design solutions will be applied: Advanced Building Envelope, Upgraded Construction Details, Advanced Fenestration, and Solar Shading. Let's start by upgrading the building envelope of the baseline building by using more advanced composite structures to enhance the thermal properties. On the cross-section of the building, the thermal insulation is represented in yellow. The designed building's thermal insulation is continuous on all parts of the building shell, and it is considerably thicker than the baseline buildings. The entire building envelope is insulated. Here you can study the cross-section of the baseline building versus the section of the building with the upgraded shell. The pitched roof composite on the baseline building is a double ventilated construction with a relatively thin thermal insulation skin that is interrupted by the rafters. The upgraded building design features a more advanced single ventilated composite structure with much thicker and mostly uninterrupted thermal insulation. The baseline building has external walls made of 400 mm thick burnt clay blocks, while the upgraded building also has a significant external thermal insulation on the outer surface of the burnt clay block walls. The thickness of the thermal breaks at the balconies has been increased for the designed building. In a similar way, the thermal insulation on the reinforced concrete external structures on the ground floor level has also been increased. The baseline building had much thinner thermal insulation there. Let's display the Energy Model Review palette and open the Structures page to see how these changes on the Architectural Building Information Model are reflected on the Building Energy Model. If an opaque building structure, for example an external roof element, is selected on the Structures list, its 3D representation is instantly highlighted on the 3D view of the Building Energy Model. In this example project, the envelope's thermal performance must be much better in the designed building than in the baseline building. Therefore, the designed pitched roof composite must also have better thermal resistance than the baseline flat roof composite solution. Let's use the Composite Attributes dialog under the ArchiCAD Options menu first to study the structural characteristics of the improved pitched roof composite. Each skin can be individually edited in this dialog in order to make the composite's performance fit perfectly into the overall design concept. Let's also review the thermal performance of the upgraded roof composite using the U-value calculator. In this dialog, the thermal properties are automatically assigned to the skins of the composite, and the overall heat transfer coefficient of the composite is automatically calculated. Naturally, these properties can be modified via the U-value calculator dialog to change the composite's overall thermal performance. The built-in material catalog can be used to assign different thermal properties to the skins or to fine-tune the assigned values based on exact building material information, such as manufacturer's data. This further enhances the simulation's accuracy, which is especially useful in the final phases of the architectural design process. As the result of the composite structure enhancement, the designed building's pitched roof has a relatively low overall heat transfer coefficient, or U-value, which translates to a relatively high thermal resistance, or R value. The next project-specific low-energy building solution to apply to the ArchiCAD BIM is to improve the constructional details. In this presentation, the balcony detail with the thermal break is used as an example. Note that we have already run the thermal bridge simulation on the baseline version of this detail in the project-specific low-energy building solution set movie clip. The advanced balcony detail features a much thicker thermal break at the balcony slab, while there is no additional thermal insulation on the external surface of the wall. Let's run the thermal bridge simulation on this improved detail using the dedicated wizard. First, we must identify the external and internal spaces indicated by blue and red respectively. All the elements of the detail are listed with their building materials on the left side of the dialog. Select the items on the list to instantly highlight them in the Details preview. We can assign or adjust the thermal properties of the individual detail components if needed. EcoDesigner Star uses a so-called adaptive mesh technology for the thermal bridge simulation. This means that the grid layout of the calculation sample points is automatically more dense at the composite junctions than at other parts of the detail. Furthermore, it's also possible to adjust the calculation grid's reference density, which makes the thermal bridge simulation faster. Let's run the thermal bridge simulation for the improved detail to obtain the corresponding linear heat transfer coefficient and result diagrams. The color-coded temperature diagram shows more consistent temperatures throughout the designed detail than in the baseline detail. The energy flow diagram only shows a minor energy flow, represented by shades of red, at the top and the bottom of the thermal break. In order to have an effect on the overall energy balance calculation, attach the thermal bridge to the thermal block where it occurs. On the Thermal Blocks page of the Energy Review palette, you can see that the example balcony detail belongs to the thermal block that represents apartment number 1. Use the Structures page to assign the previously completed thermal bridge simulation results to this thermal block, and also to specify the length along which the thermal bridge occurs. This way, EcoDesigner Star can incorporate the effects of this thermal bridge when performing the energy simulation for the building. The thermal bridge simulation results can be used very effectively during the architectural design to compare detail solutions. In this movie clip, let's compare the simple baseline detail version with the advanced version. Here are the two architectural detail drawings side by side. The baseline version is on the left. It has no external insulation and only a thin thermal break at the balcony. The advanced detail solution on the right has a thicker thermal break and a thermal insulation skin is added on the external wall. If the thermal views of the two details are placed side by side, the energy efficiency benefits can be clearly identified. In the advanced detail, the masonry block wall is protected from the dynamic effects of the external environment by the addition of a layer of thermal insulation. The thick thermal break at the balcony slab forms a continuous protective skin that envelopes the building. The masonry wall's external surface is less protected from temperature changes, and the thermal break at the slab connection is not thick enough to prevent the thermal bridge effect. Below the energy flow views, the linear heat transfer coefficients are displayed to describe the detail's thermal performance. In the baseline detail, the linear heat transfer coefficient is 3 times greater than it is in the improved detail. In other words, the baseline solution's thermal resistance is 3 times poorer than the improved solutions. It is recommended to perform the thermal bridge analysis on all critical details of the building project in order to incorporate the results of the overall building energy calculations, and also to avoid local thermal comfort issues as well as condensation problems. After upgrading the building envelope and designing more advanced details, let's see how we can improve the thermal characteristics of the fenestration. Let's select all windows on the Openings page of the Energy Model Review palette. All windows will be highlighted instantly in the 3D view. Use the Openings catalog to assign different performance data to all the windows of the project in one step. For this example building, we'll specify advanced triple glazing with high-end frames for all windows and glazed doors. ArchiCAD calculates the overall heat transmission value and the infiltration around the frame perimeter for each of the openings individually, based on the individual ratio of the transparent area and the opaque frame of the opening. As a result of this model-based geometry data takeoff, the automatically generated input of the opening's thermal and infiltration characteristics for energy simulation is very accurate in EcoDesigner Star. The overall U value for a balcony door, for instance, is slightly different from the overall U value of a window because their glazed area to frame area ratio is also different. Naturally, the infiltration around the advanced window's perimeter is also reduced to reflect the differences in applied technology for the installation of the more expensive high-performance windows and glazed doors. We also applied external blinds to all openings in the building shell. This intelligent external solar shading device is only activated during the periods of the hourly energy simulation when the internal temperature of the thermal block adjacent to the opening exceeds 22 degrees Celsius. This way, the shading device helps minimize overheating in the cooling season, yet does not cut out welcome heat gain during the heating period. Before we run the building simulation that executes the demand calculation, let's display the building systems dialog and make sure that all heating, cooling, and ventilation systems assigned to the project's thermal blocks are set to not yet specified. Note that the movie clip entitled Project-Specific Low Energy Building Solution Set contains detailed information regarding demand calculations. The goal of the energy demand calculation is to determine the necessary heating and cooling loads. If these loads are small, then the thermal conditions inside the thermal blocks are within the comfort range defined by the operation profiles. In other words, the building does its job well and provides shelter and comforts to its users without the help of the heating and cooling systems. Since building systems consume fuel, the less often they need to operate, the more energy efficient the project becomes. The designed building model, with upgraded characteristics, is ready for energy evaluation. After clicking the Start Energy Simulation button, the Simulation Setup dialog appears. Use the browser to locate the previously created external baseline building BAS file, then click Continue to proceed. Here we can import the baseline building reference file and even specify a baseline building post-processing method for the purpose of comparative evaluation. Note: for more information about baseline building characteristics, please watch the project-specific low-energy building solution set movie clip from the Graphisoft EcoDesigner Star Energy Efficient Building Design video series. After the energy simulation is completed, the Energy Evaluation Report dialog opens. Before saving it as a PDF document, let's specify the Energy Performance Evaluation Report's content. Use the list of all the available report chapters on the dedicated panel to select the ones you wish to include in the PDF document. The Project Key Values chapter is important because it contains the high-level overview of the calculation results. Let's also include the Project Energy Balance chapter in the final report. We can toggle between monthly and weekly energy balance time interval display. The Thermal Blocks chapter provides general information about the building energy model's geometry and operational profiles, while the Thermal Block Key Values chapter displays the most important energy efficiency data about each thermal block. With the help of the Thermal Block Energy Balance chapter, color diagrams showing the supplied and emitted energy flows of the individual thermal blocks can be added to the Energy Performance Evaluation Report document. We can define which thermal blocks to include in the PDF. The Thermal Block Level Output makes EcoDesigner Star a very powerful sustainable design tool in the hands of every architect. Each thermal block represents a part of the building with uniform function and orientation. The Thermal Block Energy Balances provide an excellent way to visualize how each part of the building contributes to the overall building energy model. By controlling each thermal block's performance individually, the architectural design can be optimized to the point where the project can meet even the most ambitious energy performance targets, such as LEED Platinum rating, net zero energy building operation, etc. The HVAC Design Data chapter provides very important information about the annual and hourly heating and cooling demands of the thermal blocks. This data can be used for building system sizing. The internal thermal condition data, maximum and minimum temperature values and unmet load hours, of the thermal block also appear at the bottom of this chapter. Daily temperature profiles of the thermal blocks can also be included in the report. Specific days of the reference year can be set, and the corresponding internal and external temperature profile diagrams are generated automatically for the selected thermal block. When specifying which days to display, designers usually find most useful the days of maximum heating and cooling loads and typical days representing each season, for example, a typical summer day. The Energy Consumption by Sources and by Targets chapters display information about the fuels consumed by the building systems in order to maintain the required internal comfort conditions. Currently, the fuel consumptions other than electricity appear as not yet specified, since building systems are also set to not yet specified for the energy demand calculation. Finally, let's select the Performance Rating Table chapter. This table compares the energy performance of the designed building with the baseline building. The energy use savings caused by the implementation of the project-specific low-energy building solution set also appear in this chapter. Together with the extra investment cost associated with the project-specific low-energy building solutions, the energy use savings data can be used as input for return of investment calculations. Architects can now easily execute these ROI calculations and use the results to answer one of their clients' most commonly asked questions. How long does it take until a certain solution pays for itself and starts generating profit? Let's save the customized energy evaluation report as a PDF document. Before proceeding to study the energy efficiency benefits of architectural optimization, let's recap the energy evaluation report document content in cases of demand calculation at the design development phase. These are the relevant project-level results: project key values, project energy balance, thermal blocks list, performance rating table, fuel consumption by targets and by sources tables. The following chapters contain the thermal block level results of the energy demand calculation: thermal block key values, thermal block energy balances, daily temperature profiles for the most important days of the reference year, HVAC design data. After creating the baseline building reference file, applying the low-energy architectural design solution set, and then executing the energy demand calculation with performance rating, we're finally ready to review the results and benefits of the energy-conscious optimization of the architectural design. Let's compare the energy performance of the upgraded project with the baseline project. On the left side of the screen, the results of the baseline building model analysis are presented. The right side displays the energy evaluation report of the enhanced building. The project key values chapters show that due to the building envelope enhancements, the building shell's overall heat transfer coefficient is significantly lower, about 60% lower, in the enhanced project model. As a result of the building envelope's higher thermal resistance, energy transmission is dramatically reduced. Transmission is represented by light brown bars on the project's weak energy balance diagrams. The reduced transmission causes the heating demand to decrease. Let's compare the airtightness of the buildings next. The overall infiltration at 50 Pascal pressure difference dropped dramatically from 3.46 to 1.0 ACH. Consequently, the infiltration bars, represented by light blue on the project energy balance diagram, are also proportionally smaller. There is also a significant heating demand reduction, around 50%, in the improved design. Please note that the scale of the energy balance diagrams are not identical. If you rescaled one of the diagrams to match the other, you would clearly notice that the heating bars, represented in red, are significantly shorter in the improved project design. The annual heating demands shown next to energy balance diagrams and the specific net heating energy values displayed under the Project Key Values chapter both document the dramatic reduction in heating which is a result of the advanced building envelope design. Let's review the benefits of the solar shading. Thanks to the smart shading devices, the unnecessary heat gain throughout the hot season is dramatically reduced. Please notice the reduction in the area of the yellow bars of the energy balance diagram. Consequently, less cooling energy is required during the hot periods of the year. The ArchiCAD object library contains plants with seasonal behavior. Since the program's model-based solar analysis function determines the shadow mask on each opening in every hour of the reference year, these dynamic tree object models can also be used in any design project as smart seasonal shading devices. Please check out the corresponding video clip entitled Plants Used as Dynamic Shading Devices to find out more about this standard ArchiCAD feature. The simple diagram on the screen illustrates the seasonal shading effect of deciduous and coniferous trees on the solar irradiation of openings. This very simple building has 3 large south-facing windows, and there are different types of trees in front of the building. It's visible on the solar irradiation charts that deciduous trees with denser crowns, more leaves, cast larger shadows on the openings throughout the year. Additionally, deciduous trees' crown densities change with the seasons, therefore they shade windows more effectively in the summer, although they lose their leaves in the winter and therefore provide less shading. Less shading allows more heat gain through the transparent surfaces in the cold seasons. The relative position of the tree with respect to the window is also considered by ArchiCAD's model-based solar analysis. You can note the difference in the solar irradiation charts for the different windows. The tree on the right side of the south-facing window provides shade in the morning, while the tree on the left side provides shade in the afternoon. Please note that the tree in the lowest row is an evergreen. Evergreens are non-deciduous, so they do not drop their leaves in the winter, as the corresponding solar irradiation charts clearly illustrate. Besides reducing the heating and cooling demands, the project-specific low-energy architectural design solutions also improve the internal thermal comfort conditions. Let's have a look at the thermal block of the staircase as an example. In the case of the baseline building, the staircase block must be heated throughout the entire day of February 1st. In the improved building design, however, there is no need for heating from 8 in the morning till 6 in the evening. The internal temperature displayed in light blue on the daily temperature profile program remains within the comfort zone, represented in red on the diagram, without any additional energy input. Let's compare the daily temperature profile diagrams of May 1st. A typical spring day at the project's location, the temperatures inside the staircase block of both buildings are within the comfort zone on this day. In the improved building design, however, the internal temperature is slightly higher and thus closer to the optimal comfort temperature. On a typical summer day, the baseline designed staircase block is unbearably hot throughout the entire day. In the enhanced building design, however, the internal temperature of the same thermal block is nice, comfortable, and also constant in the summer. In the fall, similarly to the spring scenario, Both designs provide sufficient thermal comfort, but the temperature in the improved building staircase block is slightly higher. Finally, let's have a look at the staircase block key values. In the baseline design, cooling is required throughout 20% of the entire year in this thermal block, while in the enhanced building design, there is no need for any cooling in the staircase block. After reviewing the energy performance consequences of the project-specific low-energy architectural design solution set, we can conclude that the enhancements have been successful in the example project. The most significant benefits come from the lower annual and peak heating and cooling loads. The performance rating table lists this data for every thermal block of both design versions, together with the energy savings achieved as a result of the enhancements implemented on the design building plan variation. The numbers speak for themselves. A 45% reduction in the annual heating demand and nearly an 85% reduction in the annual cooling demand. The office thermal block's energy balance diagram is a good example to illustrate the reduction of annual total energy flows. The result is an office with better thermal comfort conditions and reduced energy consumption. The comparison of the HVAC design data tables of the baseline building with the designed building shows significant reduction in energy demands on the thermal block level as well. Due to the improved architectural solutions, smaller building systems will be enough to maintain the required internal thermal conditions in the designed building. Let's summarize the low energy demand architectural workflow presented. Created the baseline building reference file as the basis for the comparison. Apply the project-specific low energy architectural design solution set. Performed energy simulation in energy demand calculation mode with performance rating. Review the energy efficiency consequences of the architectural optimization. EcoDesigner Star can help architects to minimize the heating and cooling energy demands, and also to optimize the internal comfort conditions for any architectural project in any climate or location.